Hi 254. In this video we're going to finish off our work in section 11.9 by finishing our discussion of curvature as well as the vectors, the tangent vector and the normal vector. So remember we have this definition already established for curvature where we talked about the rate of change of the tangent vector with respect to the unit tangent vector with respect to arc length. We came up with this in class. And then I did mention that this right here is not the exceptionally useful version for curvature because this of course requires that your curve is parameterized by arc length, which it may not be. And then we developed a new version of the curvature formula, which actually is for when we are parameterized just with respect to any variable, like t, for example. And that was this formula that we came up with, the alternative formula for curvature. So now what I want to do is come up with another way to describe curvature, which is going to be particularly useful if you're going to be talking about motion, where you're saying that your r of t is a position function, and then you can talk about its derivative as velocity and its second derivative as acceleration. So we're going to walk through a little bit of calculations here, and I've already written them out since they're a little bit heavy in terms of the writing, and I write a little bit slower with the little stylus thing than I do in class on the board. So just follow along as I sort of walk us through these calculations. So let's first of all remember that the unit tangent vector is here defined by taking the velocity vector and dividing by its magnitude. That makes it a unit vector. So what that means is that we have this relationship between v and the magnitude of v and t, right? All I did is multiplied the magnitude up times this tangent vector to get this equality right here. Okay, so now what that means is that if I take this acceleration vector here, right, which again is the second derivative of a position vector, it is the derivative of velocity, and I can rewrite that as the derivative of the magnitude v times the unit tangent vector, right, just using that equality that I just developed up there. Okay, but remember that one of our rules for derivatives of vectors says that if you have some kind of a scalar quantity multiplying a vector and you want to take the derivative, it's like a product rule application, right? So really I just say apply the product rule for taking a derivative of a scalar times a vector function. And so this little product rule thing right here is that result. So I have derivative of the first times the second plus the first times the derivative of the second. Okay, now what I want to do is use that alternative way to write acceleration, because that's an alternative way to write the acceleration right here, this line, to write the following. I want to write the cross product of acceleration and velocity. Okay, and this may seem like it's coming out of nowhere, right? But think again about what we've discussed about how the acceleration and velocity vectors look if we're talking about a path function r of t, right? Okay, crossing these two things is going to give a vector which is going to be orthogonal to both of them, right? And we'll see what we get in just a second. So if I cross acceleration and velocity, I can take this as the description for acceleration right here, put that in that box right there, and I'm going to cross it with the velocity vector. But remember, I have a way to describe velocity that I chose up here, right? Magnitude v times the unit tangent vector. Okay, so this still says acceleration cross velocity. Okay, one of our other properties we have for the cross product says that I can take this cross right here and distribute it across the addition that would be living inside of this little sort of these brackets right here. There would be like a plus right here, okay, with the terms dt or ddt of magnitude v times t plus magnitude v dt, right? That would be the stuff living in the brackets right here. So distribute that cross over the addition and I get the following statement, right? And that's this next line here where I have the derivative here, t cross magnitude vt plus magnitude v dt cross magnitude of v unit tangent vector, okay? So that's just the property of the cross distributing across the addition, okay? However, let's see if we can simplify this a little bit because I see actually, notice here that in this line right here, yes, this part of the addition right here, we actually get something really interesting happening, and let's see what happens. Let me pick a color, how about yellow? Okay, notice that right here what this actually says is that you're taking a vector and crossing it with itself, yes, right? You're doing t cross t, right? And what happens when we do t cross t? We're actually going to get a big fat 0, right? Because you're crossing a vector with itself. The reason is because the cross product is defined using a sign, and the angle that separates t and itself, right? T right here with itself, right? Okay. The rest of this is just scalars, right? Okay, this part right here is a scalar, this part right here is a scalar. Okay, so when we cross a vector with itself, we're going to get the number 0 because the angle that separates them is 0, and in the cross product we use sine, right? And sine of 0 is 0, okay? So this part right here is actually a big 0, okay? So that all vanishes away. That's all gone, right? But all we have left then is this remaining second part of this addition, right? Okay, so that's why we end up getting just this magnitude of v dt dt cross magnitude v t. Okay, so now what we're going to do is we're going to take that expression for acceleration cross velocity and we're going to do something further with it. Okay, what we're going to do is we're going to take its magnitude. Okay, we're going to take the magnitude of acceleration cross velocity. Okay, so what that means is I'm going to take the magnitude of that big ugly expression I had at the bottom of the previous page, right? So all I did is take the magnitude right here of this guy, right, which means that down here I want to just take the magnitude of this stuff, right, and that's what we have on this next page right here. Okay, so now let's use the definition for the cross product right here, because this does say the cross product of two things, right? Here's a thing, here's another thing, and we're crossing them, right, using this cross product right here. So what that means according to the definition of the cross product is I do the magnitude of the first thing, magnitude of the second thing, and the sine of the angle that separates them. So that's exactly what this line right here is saying, okay, is that I have the magnitude of the first thing times the magnitude of the second thing and then sine of the angle that separates them. Okay, now what we're going to do is just play a little bit of a game of simplifying again, because notice the vectors we're crossing, and let me get my little highlighter here again. We're crossing the vector dt dt with the vector t, right? And remember what we've done with vectors before when they're talking about being tangent vectors and stuff like that. When you take a vector and you take its derivative, you're going to get a vector which is going to be orthogonal to it. Yes, so dt dt is orthogonal to t, okay? Which means that the angle right here, this theta right here, is actually pi over 2 or 90 degrees, right? That's actually an angle of pi over 2. What that means, that looks like an n. That's funny. Let's fix that. What that means is that sine of pi over 2 is 1, which means this sine of theta right here actually equals 1, okay? Because we're using an angle of pi over 2 because we're taking a vector across its derivative, right, which is going to be orthogonal to it. So we end up getting this line simplified next, right, which is just sine theta equaling 1, and then what I've done is applied the magnitude bars to each of the components that are here, so we get magnitude v, magnitude of a magnitude is redundant, so they just sort of, it's still a magnitude. Magnitude of dt dt, magnitude v, magnitude t. Okay, now part of this still simplifies again because magnitude of t, this is a unit vector, that equals 1 also, right? So what we end up getting is magnitude v squared, since there's two of them, and magnitude of dt dt. Now we don't know that the magnitude of the derivative of the unit tangent vector is unit, right? That's not necessarily the case. The unit tangent vector can be, its rate of change can be greater than 1, right? Okay, it could be having a non-1 rate of change, right? That's just because the tangent vector has magnitude 1 doesn't mean its rate of change has a magnitude of 1. Okay, so we don't know anything about dt dt, its magnitude. Okay, however, what we do know is that dt dt is related to curvature. Okay, and this is using that formula for curvature we already came up with before in class. That curvature is equal to what? 1 over magnitude of the velocity times the magnitude of dt dt. So what I'm going to do is replace that magnitude dt dt with its equivalent, which is curvature times magnitude of velocity, right? So, long story short, and that's where we're at right now with this big so, right? What we end up saying here is we want to compare, and let me get a blue pen here. What we want to do is compare this beginning statement with this ending statement right here, okay? Because notice all the equalities right here, they connect it, okay? So what we end up saying is that curvature, that k right there, is equal to magnitude a cross v divided by, how many magnitude v's do we have? 3 of them, okay? Magnitude v cubed, okay? And this is our alternative way to describe curvature, and I think that actually is in our next slide. Yep, here it is, okay? So if we are specifically given a position of an object on a smooth curve, right, r is the position function, the curvature at the point of the curve is given by this a cross v magnitude divided by magnitude v cubed, okay? All right, let's pause there for our video, and when you come back we'll do some examples and we'll talk about the unit normal vector.